So, in the last session, we have completed the implementation of WLink list, and now we need to see how to implement a stack and queue using linked list. So, first we'll start with the implementation of stack using a linked list, and in the implementation of both stack and queue, we'll be using a singly linked list. We'll be making it of SLS. Okay, so now for stack. As we all know that a stack is a linear data structure in which the data is inserted and removed from the same end. That end is called as a top of a stack, and it follows a structure called LIFO, last in, first out. So whatever is inserted last, that will be removed first. Okay, and that is your stack data structure. Now, we have seen the implementation of stack using arrays, and today we'll see the implementation of stack using linked list. Fine. So for linked list, we all know that we need to make use of a referential structure, and now we'll be having a referential structure for a single linked list with single pointer, and we are calling that structure as stack. Okay. So in the array implementation, if you remember, so we had a structure called stack, and inside that structure we had one array, and we had one variable called top, which used to store the index position of the topmost data element. Now here in this case, we are having a structure stack, and into this basically this is a node itself. Okay, so it has a data part and it has a next pointer pointing to the next node. Now, once we have this structure in place, then we need to see that which all operations we need to perform. Now, when we think of a stack, so we have different operations available for stack. For example, initialization of stack, checking whether the stack is empty or not, checking whether the stack is full or not. Then these are the basic operations. The most important operations are the push, pop, then peek can also be considered as one of the important operations. Then you have display. Okay, so 3 to 4 operations are basically important operations for the stack. So one is a push, that is the insert operation. Then the pop, that is the delete operation. So in push, basically what do we do? We insert element at the top of stack. Of course, if the stack is not full. Okay. Now, when we think of implementing this operation of a stack using linked list, so basically we are visualizing a list, a single linked list, SLL, and you want to push a data element. So basically here it is equivalent to a insert operation of SLL. Okay. Now, if you remember, then we have different variants of insert operations. For example, we had one function, say insert at end, then we had another function insert at beginning, then we had insert after, then likewise you can have insert before. Okay, so these are the different possibilities with the insert operation on single linked list or in general on a linked list. Now, when we visualize a stack using a list, so a stack is a data structure in which insertion and deletion is done from the same end. And that end is called as the top of a stack. That end is called as a top of a stack. Now, can you tell me that if I want to uh, compare the push operation of a stack with this insert operations on a single linked list, then which operation on a single linked list or which function basically, which insert function of a SLL resembles the push function of a stack? I repeat, out of 4 insert functions, insert at end, insert at beginning, insert after, and insert before. So out of these 4 functions on SLL, which function resembles the push function of a stack? Come on, post your answer onto the chat box, or you can simply unmute your mic and think about it. and let me know which insert function of SLL resembles the push function of a stack. There are some answers, and people are saying insert at end, insert at end, insert at end. There is one end which is open in a stack. If you think of a stack, so stack is a container or a box in which, if you see these two ends, one end is on upper side on top, and another end is at the bottom. Okay, so stack is a data structure where one end is closed. So this end is closed. Okay, so you have only one end open, which is the top of a stack, which is the top of a stack, and from this upper end only your data is going to get inserted and the data is going to get removed. Okay, and this top of a stack is something like my head pointer of a list. I repeat, the top of a stack is nothing but something like a head pointer of my list. Okay, so I can easily replace my head pointer with top. I repeat, I can easily replace my head pointer with my top pointer. So basically, my head pointer of list becomes a top of my stack when I implement a stack using list. Okay. So in this case, now you need to tell me that which insert function of SLL resembles the push function of a stack. Insert at end is not a correct option. Insert at beginning. Yes, insert at beginning is a function which resembles the push function of a stack. Why? Because your head pointer is acting as a top pointer. I repeat, the head pointer is acting as a top pointer. So my head pointer is pointing to the first node of a list. Okay. And so my top pointer is also pointing to the first node of the list. So my insertion will be always at beginning, at beginning, at beginning. And likewise, if I talk about the remove function, so which remove function resembles the pop operation, whether it is remove at end, remove after, remove before, remove given, or remove at first, remove first. Remove first resembles the pop operation, or remove last resembles the pop operation. Which remove function resembles the pop operation? Can you tell me? My top is pointing to the first node. So insert at beginning is a function which resembles the push operation. Likewise, which remove function resembles the pop operation, whether remove first or remove last, which will resemble the pop operation. Yes, come on. Yes, remove first. Definitely, remove first will resemble, because your top is pointing to the topmost element. It is something like your head pointer. Okay, so you are going to insert from the top and you are going to remove from the top. Insert from top, remove from top. So insert at beginning and remove first. Insert at beginning and remove first. Okay, so this way you are going to implement the stack using list. Now, if you see carefully, so see here what we are doing. So my push function, this push function is basically simply a copy of my insert at beginning. Okay, exactly insert at beginning, nothing else. So what we are doing into this, simply like your insert function, pass the head pointer or the top pointer of the list in which, or stack in which you want to insert, and obviously the data which you want to insert, it will return what? Pointer to a stack. Fine. Then we are having a few dummy pointers, just like your insert at the beginning, then allocating a space. Now, this is important to understand from conceptual point of view. We are allocating a space, so we are making use of a malloc library function. We are calling the malloc library function. It will allocate a space to you, and it may not allocate a space to you, depending upon different possibilities or different conditions. Now, see what I am doing here. If p equals null, If no space is allocated, so in that case, I am simply printing a message stack overflow. Can someone tell me what does it mean? Come on. I am checking a condition. If P equals null, then I am simply throwing out a message stack overflows. It is nothing but stack is full, something like stack is full. Now, since stack is full, stack overflows, so we cannot perform the push operation. It is as good as that. Exactly. This is nothing but not enough memory. If memory is not allocated, if malloc function, if the malloc function do not do not allocate a space, so it will return a null value for any reason. Okay, for any reason, when malloc function do not allocate a space, so it will return a null value. That null value will come into P. Okay, that null value will come into P, and if P has a null value, it means that space is not allocated. And when a space or memory is not allocated, then only we can say that the stack is full and now we cannot create any more node at this point of time. And that's why the message is stack overflows or stack is full. And this is the only condition when you are implementing a stack using linked list. I repeat, this is the only stack full condition when you are implementing a stack using linked list. Otherwise, it is a dynamic memory allocation. You do not know when your stack would be full. When you are implementing a stack using arrays, so it's a static memory allocation. You can check for the size of the array. If the size of the array has been done, if the array is full, then you simply say that your stack is full. But in this case, what we are doing, we are implementing a stack using linked list, which basically makes use of a dynamic memory allocation. It's a dynamic structure. It can grow dynamically, it can shrink dynamically. It grows with the help of malloc library function, and it shrinks with the help of free library function. Okay. So since it grows dynamically, so we do not know how big it will grow. I repeat, since the data structure is growing dynamically, so we do not know how big it will grow, how long it will go. Okay, so since we do not know how big it will grow, the only point remains with us is to check the return value of the malloc function. If the return value of the malloc function is null, so now we come to know that a memory cannot be allocated, and that's why we say that now the stack is full or the stack overflows. And this may absolutely differ from machine to machine, from scenario to scenario, and so on. So there are n number of parameters on which this will be determined, whether your malloc function is returning null value or it is returning address of the allocated block. So there are n number of parameters. We do not go into the detail of that, but what you need to remember that when a malloc function returns your null, then only we say that the stack is full or the stack overflow. Okay. Else there is a space and you cannot you can allocate. There is a space and you can push a data. Okay. So in the else part, we create the data part of the node. So P of data equals to D, and then this is insert at beginning, and this is SLL. Okay. So insert at beginning, simply we are doing P of next equals to H and H equals to P. Absolutely simple. Okay. Now, when we were implementing those function of SLL and even for DLL, so I said you quite straightforward that though we are implementing in one way, there is still possibility of implementing the same thing in little different way. Okay. And with different way, you can reduce the number of lines or you can increase the number of lines. You can make your code compact or you can make your code simplified but little bigger and so on. There are different possibilities. Every programmer can think differently. Every programmer can come out with a different solution for the same problem. It is absolutely fine. I do not stop you there. In fact, I appreciate you if you come out with a different way of doing the same thing. But yes, that way should be a better way than the already existing way. Okay. So if you see this code, so I think this is straightforward and this is quite simple. And it is reducing the number of lines also. Okay. And I hope that it is taking care of all the conditions, whether the list is empty or whether the list has already few nodes and so on. Okay. So what we are doing, simply we are writing P of data equals to D, P of next equals to H. So my this new node becomes the first node when I write P of next equals to H. And then I change my head pointer by simply say H equals to P. And then I'm returning the head pointer that is H. And this head pointer, for your kind information, is the top. The head pointer is basically the top pointer. Okay. Then the next is your pop function. Basically, we need to take care of these two functions only, and then remaining, I think you can very well do yourself. So the pop function, it resembles what? It resembles remove first. Uh, resembles remove first of SLL. Okay, and this I can say the push function resembles. Okay, insert add back of SL. Okay. So the pop function resembles the remove first. So we are going to remove the first node of the list. And before removing the first node, before performing the push operation, you need to check whether the stack is full or not. And this is an implementation using a list. So what do? We check for the return value of the malloc. If the return value is null, we say the stack overflows or the stack is full, and then we cannot perform the push operation. In the else part, we perform the push operation. Likewise, when you talk about pop, so if there is something in the stack, then only you can pop. Okay. So you need to check for an empty condition. Now, again, this is an implementation using list. So the empty condition is simply if your top pointer or your head pointer is null. I repeat, if the head pointer or the top pointer is null, so we say that the stack is empty and you cannot perform the pop function. So that's what we are doing here. If h is not null, if the given top pointer, this h is not null, then only you are going to pop something. Else, we are saying stack underflows or the stack is empty. Okay, one and the same thing, stack underflows or stack is empty. So let's see what we are doing into this if part. We are creating a temporary pointer, temp equals to h, because we need to free it. And then h equals to h of next. So h starts pointing to the second node, whichever is the second node. If there is no second node, if there is only one node, so the next pointer of that node would be pointing to null because this is using SLL. So h would become null if there is supposed to be only one node. If there are multiple nodes, then h would be pointing to the second node. And then we are setting the next pointer of the first node as null. The node which was earlier the first node, that's its next pointer to null. And then we are simply saying popped, we are printing a message, popped data is the data part of temp of data. And then we are freeing the memory which is pointed by the pointer temp. So free temp, that's all that. So this way you are popping an element from the stack, or you are popping the node basically from the stack. And if you see this, so you may find it little different the way it is implemented over here. I am saying you that it resembles the remove first function of SLL, but here you can say it is implemented in a little different way. But this is how we keep on improving the code, and this is how we keep on improving the thing. So this is our pop function. Then the display function, and for your kind information, displaying a stack is always from top. So by default, we display from the first node, and the way we are implementing here, that is insert add beginning and remove first, push pop both from the same end. So from that on end only, we are going to display the stack. So that way we are going here. So if my stack is not empty, so I would say stack content, and then while time not equals to null, it is as good as your display function of SLS. Print as in the data part, then temp of data, temp equals to temp of next. Then close the while loop, close the if else stack is empty. Okay. So a very simple implementation of a display function. Uh, you want to display any more information with this? This is simply displaying the content of the stack. You want to display the next pointer, or you want to display the address of a node, then you can do so. The way we did for the SLL and DLL both. Okay, then comes your main function, and inside the main function, very important thing. Now you have a top pointer. The way you had a head pointer for SLL and DLL. Now for the stack implementation using a list, that pointer is called as a top pointer. So if I am having one stack, so I am having one top pointer. If I am having two stack, I will be having two top pointer, top one, top two. If I'm going to make use of three stacks, I will be having top one, top two, and top three. And if I want to go for n number of stacks, then I can go for the array of pointers of this structure type, or I can go for double pointer. It's up to me how do I implement it. For example, I can go for array of pointer. So array of top pointer, a top, and say I want to create a pointers of say 10. So using this array, now I can manage 10 stacks. How many stacks I can manage? Total 10 stacks. Okay. And here I can manage one stack. It's a single pointer. This is an array of pointers. I repeat, this is an array of pointers. And how many elements are there into this array? 10 elements. So basically those 10 elements are 10 pointers. 10 pointers to structure stack. 10 pointers to structure stack. Each pointer will be pointing to one stack. Okay. So a top of 0 is one pointer which will be pointing to one stack. A top of 1 is another pointer which will be pointing to second stack or another stack. Likewise, a top of 2 and so on up to a top of 9. So basically you have 10 pointers in this array. So you can manage or you can handle 10 different stacks using linked list. Okay, using this array pointers. So this you can do if you want. I'm simply handling one single stack, so I'm having only one top pointer. Then few dummy, and then I'm making top equals to null, and this is nothing but initialization of my stack. Initialization of stack pointed by top. Okay, then we have our favorite infinite loop, a menu-driven code. Here we have the options. I'm putting one interesting option for you people called unlimited push. So I got a push function, I got a pop option, I got a display option, and then finally I have the exit option. And before the exit option, I got one interesting option called unlimited push. Okay, this will see what does it mean. Then we have the cases. The first case is a push. So simply we ask for the data from the user. We take it into a variable D, and then we are calling the push function. the way we call your insert at beginning function. So it was head equals to insert add beg, then in parentheses head comma d. In the same way here, the head is basically the top. So we say top equals to the function name is push. So top equals to push in parentheses top comma d. Okay. Then break. Then the second option is pop. So again, it is simply something like your head equals to remove first in parentheses head. So here we have top. So top equals to pop in parentheses top. Then the third option is your display, and we need to pass only the top point of the stack. So display top. And then there is a fourth option. I will let you know what is the fourth option, that is unlimited push. Before that, let us compile this code, let us execute it, and let's see the output. Okay, so my code got compiled. This is session 26. Application is available, and this is our program. So I go for some push operations, and I pushed first 10. Then I perform one more push operation. I want to push 20, and wow, what is the spelling of the display over there? I go for the third option, which is display, and the stack content is 20 and 10. 20 is on top of my stack. If I want to perform one more push, then I push say 30. 30 comes on top of a stack. There is no message after the push operation gets successfully executed. So it's up to you to need to make some changes over there. I go for display, and 30 is on top, so I got 30, 20, and 10. Now let's pop something. So pop the data is 30 because 30 is on top. Sorry, 30 is on top, so 30 has been popped. And if I display, then I should have only 20 and 10. So yes, now 20 is on top, and I have 10 at the bottom. I go for one more pop, and 20 is popped. If I display, there should be only one element. Yes, it is only 10 now, single element. And then I go for one more pop, and popped element is 10. 10 has been popped, and there is nothing in my stack. So if I try to display the content of my stack, so it says stack is empty. Absolutely fine. Stack is empty. Okay. Now if I try to pop, second option, it says stack underflow because there is nothing in my stack to pop. Okay. So I can again push and I can do the things. Now let me check. What's the problem over here? And let me show you this unlimited push. What is this unlimited push? So this is nothing but making an infinite loop, and into an infinite loop, I'm simply calling the push function. So while one, then top equals to push top comma 10. So I'm constantly pushing a constant value that is 10 into my stack. Okay. And when I say I'm constantly pushing, so I mean to say basically infinitely pushing. Indefinitely I'm pushing it. Okay. So it is done with the help of a while loop. This is only done to understand that when my stack gets full, when my stack gets full. Okay. So just to get a rough idea. Now, what would happen that your program will get into some infinite loop if we call out this option, and it will keep on executing, it will keep on executing, and at some point it may come out. At some point it will come out of execution when no memory can be allocated to your program. Okay. And there are n number of things which can be responsible for this. So basically, we do not know. So let me call that function, and let me first push something. For example, if I'm pushing 10, sorry 5, into my stack, and if I display, so 5 is there into my stack. Now I call up the fourth option, that is unlimited push, fourth option. And there I'm saying really unlimited, a question mark. Okay. So basically, is it really an unlimited push, or I'm simply theoretically calling it unlimited push? As I said, you our program stuck in the sense it is now into an infinite loop, and it is simply allocating the spaces. It is creating a node 10, 10, 10, 10, 10 continuously. Okay, or you can say infinitely into an infinite loop. We are calling the push function. So for every push function, it is creating a node. Okay, using the malloc function, and then it is attaching that node at the start of a list. So basically, your list is growing, and it is growing quite big. Okay, it will keep on growing. It will keep on growing till it reach the space when your malloc function do not allocate a space to you, any more space. Okay, when the malloc function do not allocate a space, then we should get a message that stack overflows. So basically, we are waiting for that message, and we do not know that when that message may come, or even in between your program may get terminated. It depends upon a number of conditions, as I said you earlier, and it may vary from system to system. It may vary from current load on a system and so on. So let it be keep executing there. Meanwhile, we can. Oh, my machine got hanged. No. Hmm. Done. So what you can see here, that my machine got switched off. I don't know how. Uh, oh, so now I am getting a message that your PC ran into a problem and needs to restart. We are just collecting some error info, and then we will restart for you. 35% complete, 45% complete. So this is how Windows operating system is handling the situation. Likewise, your different operating system may handle it differently, but my machine got restarted. My Windows system got restarted when I executed that into an infinite loop. And for your kind information, it was not any simple function into an infinite loop. It was a function which was having a malloc function call. Okay, so basically, there we are continuously allocating a space. Continuously, we were allocating a space. Okay, so my machine got restarted now. You can try that code on your machine. You can see what happens. You can try it on Windows. You can try it on Linux. Please let me connect. Okay, so now I got connected. So this is the implementation of stack using list, and we tried for an infinite push so that we can understand that when does we get this stack overflow. But unfortunately, my machine got restarted before I get that message, and I I suggest you also please try this option on your machine and see what output does it give to you. how does it behave. Okay, so I will be sharing this code with you, and this is session 26. So we stop our session for the day. Let me stop the recording.